Today we're going to cover section 6.3, the arc length. You first learned this in trigonometry. Because up until now, we've looked at algebraically the length from one point to another point. This is point 1 to point 2. The length or the distance between 2 points. How do we find in algebra, how do we find the distance between point 1 and point 2? Not the slope. Let me give you a hint. That's slope. Pythagorean theorem. The hypotenuse C is the distance between point 1 and point 2. That's not a problem. That's pretty easy. We do that straightforward. The problem comes when we have a curve. So the problem comes when we have a curve. Notice also, whenever we talk about the stuff, we always talk about continuity is an important factor here. Continuous curves are paramount. Because if we have a discontinuity somewhere along it, then we have other issues we have to worry about. So for right now, we're only going to concern ourselves with continuous functions, continuous curves. So we could look at the secant line and figure out the distance between point 1 and point 2. But is that going to be the accurate distance of this curve? No. Because the Pythagorean theorem, the formula we just had, would only find this length here. And obviously, this length here, which is what is called the arc length. The arc length is longer in this case than the distance using the quadratic Pythagorean theorem. So the question now becomes, how can we use this straight line method to best approximate the length of this curve from point A to point, or from point A to point B? How do you think we could go about doing it? What are some possibilities? Think about what we did in calculus already. Riemann sums, exactly. What did we do in the Riemann sums? We took, to find the Riemann sum, the area under a curve between point A and point B, we cut it up into small pieces found the area of each one of those pieces, and then added them up to get the area under the curve between those 2 points. So we went, as delta x got smaller and smaller and smaller, the number of the slats became increasingly large. So we're going to do the same thing here. Between our point A and point B on our curve. Also, another thing is our function is continuous on the closed interval AB. The reason we're using the closed interval AB because it'll be much easier for us to find the total area under the curve because we can now include these end bars. Okay, so let's look at terminology here. F is continuous on this closed interval. We say that f of x is smooth. Since the function is smooth, meaning there's no discontinuities in there anywhere, the graph of f of x is a smooth curve. You'll hear those words a lot used in calculus. It's a smooth curve. It's a smooth function, which means that there's no discontinuities, no anomalies of any sort. So what we have to do between A and B, we'll call this one x sub 1, we'll call this one x sub n, because what we have to do now is we have to carve this up, partition this into a whole bunch of slivers. Where we have A is less than, well, let's call this an x sub 0. A is equal to x sub 0, which is the far left point. B is equal to the x sub n, the far right point. So everything in between has to keep on growing. So this is x sub 1, x sub 2. Now, how's that going to help us? If we just look at up here really close, we have our curve. We have our slivers. This is the sliver of x sub 0. This is of x sub 1, x sub 2, x sub 3. Where these slivers intersect the curve, we call those the points. There's point 1, there's point 2, point 3, point 4, all the way up to point N. We're going to use these points the same way we did in linear equations. We're going to connect those 2 points by straight lines and add up all those little distances. So we're going to find the distance. We're going to add up the distances from P1 to P2 to P, so on and so forth. So what we have to do is we have to define a delta x. Since we have from x sub 0 all the way to x sub n, we're simply going to take x sub k minus x sub k minus 1. Basically, like delta x will be x sub 2 minus x sub 1. X sub 5 minus x sub 4. That's what that means. And the corresponding y values, the delta y, will be done the same way. Y sub k minus y sub k minus 1. Because together these two are going to tell us the length of each of these sections. So the distance between pk and pk plus 1 is equal to L. And of course, we use the Pythagorean theorem for that. Well, C is equal to the square root of a squared plus b squared, the square root of that. Where the hypotenuse is the L, the A is the horizontal, so that is the delta x squared, and the y is the vertical, which is the delta y squared. So those are each of the points. Since we have so many of them, we have to break them up into sections. So it's x sub k squared plus delta y sub k squared. And there's your formula that we'll be using to find the Riemann sum, or the sum of all these little lengths, distances that we found. So far, so good. It's the same thing we did earlier to find the areas under the curve. Now we have to convert this formula into the Riemann sum. Because our first step, so what does this represent? This just represents the length between pk minus 1 and pk. That's what each of these represent. What do we have to do with all those? Add them up. Okay, so we have to add them up. So the first thing we have to do is we have to add up from k equals 1 to n all the lengths. In other words, what that means is we have to add up all the sub k's from k to 1 to n, all the distances, delta x sub k squared plus delta y sub k squared. Okay, the problem with this is if the whole line is above the curve or below the curve, then we have a larger error factor. So the best way for us to figure these out, because if we draw a line between here, our line is underneath it. So for the best thing we can do is between, let's say, x1 and x2, we can find a point that's halfway between there and use that as our value. Remember, we have to now relate this to the function itself. We call this C1. That came from the intermediate value theorem. Not the intermediate, the mean value. Mean value theorem simply states that between any x1 and x2, there is a point between there. Or in general, ck and xk, k plus 1, there's a ck in there. But we figured out the delta x. That's not a problem. The problem is, because remember, we have to find the area of these slivers. We have delta x. That's not a problem. The problem is the delta y. How do we calculate the height? The height of the function comes for the function itself times your delta x sub k. And then since we're looking for the midpoint of the mean value, the average of those 2 points, that's what's going to go in here. So we're going to have, so delta y sub k is now defined as our function at the c sub k, delta x sub k. Now we have the height. We have the height, we have the width, multiply those together, and now we have the area of that curve. That's the derivative of it. It's a derivative of it. Let's see what we have so far. We have the summation of our lengths, which is equal to delta x sub k squared plus delta y sub k squared. Then we went ahead and defined delta y as f prime of c sub k delta x sub k squared. Now, that's what we just defined it up here. Delta y is that. Algebraically, we have delta x sub k squared, and then we can distribute this throughout there, so we have f prime of ck squared delta x sub k squared. I distributed the 2 into both of those, so I don't have a parenthesis on the second one. These two delta x's I can factor out. So I took out delta x, let's put out, I can put it out in front. So I have the 1 plus f of x squared inside the second parenthesis. But what I have now, because this since they're multiplied, I can split them up. So I have the 1 plus f prime of ck squared. The square root and the square cancel, so I simply have a delta xk outside. So this is what my length is equal to. That's my length formula. Is this function continuous? Are there any anomalies in there? Any asymptotes? Well, first off, the derivative is squared, so that can never be negative. So the inside can never be negative, so it's continuous. It's a smooth curve. So since it's continuous on our closed interval AB, we can, to do the Riemann sum, we have to do what with these summations? There's one thing missing to be a Riemann sum. We have to take the limit of both of those. So we have to take the limit as n approaches infinity of our summation of k equals 1 to n. Okay, now, question. Why do we take the limit from n goes to infinity? Well, yeah, because k goes from 1 to n, and k is the summation of all the lengths. So if we're going to infinity, that means we have very, 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 very infinitely small lengths. It's so close to become just points. We're adding all the points. So that's the reason we go from whatever that boundary is, and these go with k. So this becomes the limit as n approaches infinity. The summation of k equals 1 to n. 1 plus f prime of ck squared delta x sub k. Since the limit of the summation of this function is continuous and smooth, and we can do a Riemann sum, that means we can now take the integral of it from a to b, from our closed interval. So now instead of doing the bounds, which we're changing the limits of the summation of the delta x. That now becomes dx since we're integrating it. And instead of the c sub k, it's just x because we're integrating with respect to x. Now I'm gonna give you a definition first, formal definition, and then we'll do some examples. Of arc lengths. Which again, if you think about this is very interesting. Is we're defining a curve using straight lines. We're defining a curve by using lines, which is counterintuitive. We also, in algebra, defined a circle with using triangles. So it's so cool how everything relates to itself. So, in a definition of an arc length, let f of x be a continuous smooth function on a closed interval AB the length of the arc, the arc length of the curve You could also say instead of arc length, you say the bend of the curve. Y equals f of x from point A to point B, where A is equal to, on the x-axis, so this is f of A, and B is equal to B f of B. The length of the curve from point A to point B, where is the value of the integral A to B 1 plus f prime of x squared dx is equal to the integral from A to B 1 plus dy dx squared dx. That's the definition of an arc length. Where's my example sheet? There. Everybody got this? Now for some examples. Find the length of the curve shown below of the function y equals 4 radical 2 over 3 x 3 halves power minus 1 between x goes from 0 to 1. So what's the first thing we have to do? We have our y. What's the first thing we have to find for our, remember, what formula are we using? To find the length of the curve, this is the arc length. What's the formula for arc length? So inside here, what's the only thing we need to know? We know what A and B are. A is 0, B is 1. We have to find f prime. We have to find the first derivative of this function. So we have to find y prime. Again, that's a constant. So we have 4 radical 2 over 3. The derivative of x to the power 3 halves. The 3 halves comes down, and you subtract 1. So 3 halves minus 2 over 2 is 1 over 2. And 1 disappears. The 3's cancel. The 2 cancels with the 4. So we have 2 radical 2 x to the power 1 half. So now we have the derivative. What else do we need to do? Plug it in this equation. What else do we need? Because remember, y prime is dy dx is the same thing as f prime. What do we need now in this equation? We need to square this. So this it gets distributed to every member. So we have 2 squared, square root of 2 squared, x to the power 1 over 2 squared. Two squared is 4. The square root and the square cancel, so that's just 2. The 2's cancel, so we have just x. So the answer is 8x. Now we can plug this stuff in. We have what we need. Now plug it in there. Formula. L equals the integral from 0 to 1 plus 8x dx. This equation looks a lot easier to work with. How are you going to do this? What's that? Yeah, but how are we going to take the integral of this function? We did this last chapter. Substitution, very good. Let u equal 1 plus 8x. And what's du going to be? So we're going to have u to the power u to the power 1/2 du. One half integral that you have to add 1 to it. So we have u 1/2 plus 1 over 1/2 plus 1. That's the outside. Leave the inside alone. That's going to be u. And then du is going to be 8. But we don't have an 8. And so what are we missing? We have to put an 8 there. So we have to have 1 over 8 out in front. So on the bottom, this is 2 over 2. So it's 3 over 2. So that's going to be 2 over 3 from the bottom times our function 1 over 8, because we had to put an 8 inside there, times u, which is 1 plus 8x to the power 3 over 2. and we integrate that. That's our integral. And since we don't have an 8, we need an 8 there, so we have to put a 1/8 in front. Oh, let's look at this. Well, this is a constant. This will cancel, so it's 4. So it's going to be 1/12. 1 plus 8 to the power 3/2 minus 1 plus 0 to the power 3/2. Nine to the 3/2 power, 1 to the 3/2 power, so what this means is we have square root of 9 cubed, which is 3 cubed, which is 27, 1. So you have 1 over 12 times 26. They both have a 2 in common. 13 over 6. There's the arc length of that curve from 0 to 1. Any questions about it? So the hardest part is remembering that you use substitution if you have to. Again, if this formula is in your chart somewhere, the cheat sheets, you can use those as well. Let's look at example 2. Find the length of the graph of x cubed over 12 plus 1 over x from 1 to 4. F of x is x cubed over 12 plus 1 over x. What's the first thing we find with this thing? Let's find f prime. The derivative of this first one is 3x squared over 12. This one becomes -1, so it's -1 over x squared. So it's x squared over 4 minus 1 over x squared. That's our first derivative. Our formula is that. This is A and this is B. So it's going from 1 to 4. And our f prime is x squared over 4 minus 1 over x squared dx. So what's next? We have to square this thing here. So let's look at the inside of this whole thing here. One plus x squared over 4 minus 1 over x squared. We have to FOIL this one because it's got a sum plus or minus in the middle there. So it's going to be x squared times x squared is x to the 4th. 4 times 4 is over 16. Minus 2 times x squared over 4 times 1 over x squared. The x squares cancel. The 2 and the 4 cancel. So it just becomes minus 1/2. And then plus x squared times x squared is x to the 4th. Combine like terms. 1 minus 1/2 is a positive 1/2. Can we go any further? Yes. Because if you look at this term is x squared over 4 squared. This term, 1 over x squared squared. And the middle part is 2 times this is 1/2. It's a perfect square, actually. I'm getting to. The first and last term are squared, and the middle is 2 times the first term times the last term equals the middle term. X squares cancel. 2 goes into 4 twice, so it's 1/2. So this becomes x squared over 4 plus 1 over x squared squared. It's a perfect square. Now, why was that important? It was very convoluted, but it's important because now, where does this equation go? This equation goes in place of this inside there. So instead of 1 plus this, I now have the square root of x squared minus 4 plus 1 over x squared squared. Which the radical and the exponent cancel. X squared over 4 minus 1 over x squared dx. It made it much easier for us. Because now, when we take the integral of both of these parts separately, the integral of this first part is x to the 5th over 5. Well, I take out the 1/4 times 1/4. X negative x2, so it becomes x to the power negative 1 over negative 1. Oh, I'm sorry, it's x squared. It's not 5, it's 3. So it's 3 over. So this first one becomes x to the power 3 over 12 or plus 1 over x. From 1 to 4. Any questions so far? Yeah, so I forgot. I thought it was x to the 4th. No, but it's x squared. So it becomes 3 divided by 3, and that's in 4. 4 cubed over 12 plus 1 over 4 minus 1 over 12 plus 1. So we have 4 times 4 times 4 here. So it cancels with one of those. So 16 over 3 plus 1 over 4. This is 12 over 12, so it's going to be 13 over 12. Multiply this one by 4, and this one by 3. 64 plus 3 over 12 minus 13 over 12 67 over 12 minus 13 over 12 is 54 over 12. Yeah, it should be plus. Okay, where did that number doesn't look right. So we have x cubed over 12. Ah, that's where it was. It should have been minus. Minus. So therefore it becomes 16 over 3 minus 1 over 4, 1 over 12 minus 1. Okay, that looks better. So we get common denominator is 12. 64 over 12 minus 3 over 12. So we have 76 minus 4 is 72 over 12. There. Yeah, because here, when I took the integral of this one, it changed the sign to a negative. That's what I carried on. Luckily, it only happened at the end. All right, let's look at the next example. Find the length of the curve y equals 1/2 e to the x plus e to the negative x from 0 to 2. Remember, we're trying to get to this. So we have to find the first derivative. The derivative of e to the x is e to the x. E to the negative x is negative e to the negative x. Because the derivative of e to the x is the derivative of the exponent times e. And this is a, and this is b. So that was our first step. So from 0 to 2, 1 plus 1/2 e to the x minus e to the negative x squared dx. So we square this now. We get 1 to the 4th And now we have to FOIL this one. So we get e to the 2x plus ex times ex is e to the power 2x minus 2ex e negative x plus e to the negative 2x. Everybody see where I got this from? I just FOILed this one. E to the 2x. These two, since they're multiplied together, I add the exponents, I get e to the 0, which is 1, so I just get that. So that is my y prime squared. Now we got to do this whole interior part. So it's 1 minus or 1 plus, I'm sorry, 1 plus. 1 plus 1/4 e to x minus 2 plus e negative 2x. Distribute e to x over 4 minus 1/2 e negative 2x over 4. Combine like terms, 1 minus 1/2, so I have e 2x over 4 plus 1/2 So if I factor out a 1/4, I got e 2x plus 2 plus e negative 2x. E to 2x, e to 2x in the middle, that's 2 e to 2x. So e 2x plus e negative 2x squared. That's a perfect square. That times that equals that. No, those would be gone. Right. Yeah. So we square them. Yeah. All right. So now we take this part, plug it back inside here. 0, 1/4 EX plus E negative X squared dx. Yes. This one on the bottom? Yeah, because as I'm looking at this, this equation here came from EX squared. This one came from E negative X squared. And if you multiply these two together, you get that 2EX negative X. So it's a perfect square. Okay, so square root of 1/4 is 1/2. And the square root of that, so it's EX E negative X dx. Once we get to something like this, it makes it much easier for us. So what do we do next? Now we integrate it. This is a constant, so it can go out in front. Integrate EX, integrate E negative X. What is the integral of E to the power X? What is the integral of E to the X? E to the X. And the integral of E to the negative X? From 0 to 2. So our length is going to be 1/2 E squared minus E negative 2 minus E to the 0 minus E to the negative 0. 1 minus 1 is 0. Remember, E is 2.71817, whatever. It's a constant, so plug in your calculator, you get a value. But I'll be happy to get this far. So far, so good. Yeah, I'm not going to say it's easy because the algebra is very difficult. Being able to go from one point to the other. You notice what we did here. At this point here, after we found our derivative squared, we try to take the entire inside. And if everything works out right, this entire inside will become a perfect square. So that'll get us out of the radical. So if everything works out right, that's what should happen. Okay, what if we don't have what if we don't have a continuous function? What if there's some discontinuities, jump discontinuities, or whatever? Change the not the order of integration, but change the integral from dx to dy. And here's the formula for the length of x equals some function gy from C to D. Remember, f of x was a continuous function with respect to x. Since we're changing our order of integration, we're now going from x to g of y. And that's why we're using g instead of f. So if our g of y function, if our g function is continuous on our closed interval now of CD, the length of the curve x equals g of y from point A to point B where A is equal to G of C and B is G of D. Is the length from C to D 1 plus dx dy squared dy is equal to the integral from C to D of 1 plus g prime of y squared dy. It's the same thing. It's just now we have to change from x to y. A little bit more happens to that because we also have to change the bounds of integration. But there's a formula. So let's look at an example. Find the length of the curve y equals x over 2 to the power 2/3 from x equals 0 to x equals 2. What do we do first? Let's first find out why we have to change it. Let's first pick up from where we left off. Let's first find the derivative of y. So if y equals x over 2 to the power 2/3, the derivative is 2/3 x over 2 to the power negative 1/3 times the derivative of the inside. The derivative of the outside times the derivative of the inside, which is 1/2. Which equals the 2's cancel, so we have 1/3, 2 to the x to the 2, or positive 1/3, because we took this and flipped the inside. So what is wrong with this equation? Remember, we took the derivative, we got x over 2. We got a negative exponent, so we have to change the sign from negative to positive, so we have to flip the inside, so we have 2 over x. What is wrong with that? Yes. That is the indication. If it's not integrable at any point within the domain, the closed interval, then we can't use that. So we have to switch it now. So let's switch it. Y equals x over 2 to the power 2/3. Solve for x. What's the first thing you have to do? We have to get rid of this exponent. We have to make that equal to 1. How do we do that? Raise both sides to the power 3 over 2. So that cancels. So we just have x over 2. Then multiply both sides by 2. X equals 2. Y to the. So this is our new equation. We also, at this point, we have to change our bounds. How do we do that? Using these, how do we do that? Well, set x equals 0 and set x equals to 2. How can this function ever equal 0? Is if y equals what? So that's our c. And the other one, when set equals 2, divide both sides by 2. 1 equals y to the 3/2. So y is equal to 1. That is our d. So we have our function. We have the bounds of integration. So now we just have to go ahead and do the work. Any questions so far? So let's begin. So the L is equal to C to D of 1 plus dx dy squared dy from 0 to 1, 1 plus, okay, there's x. We have to find the derivative, then we have to square it. What's the derivative of x? So, so we have a 2 out in front. The derivative, bring that down. 3 over 2. And subtract 1 makes it 1/2. So the derivative of x is 3y to the power 1/2. When we square it, three squared is 9. Y to the power 1/2 squared is simply y. So this is just 9y. Remember, we have to find the derivative squared. So once we transposed it from y equals to x equals, take the derivative and square it. Now we have to integrate it. How do we integrate this? Using which method? Yeah, use u. U du. So we need to have a 9 out in front. Do we have that? No. So I got to put a 1/9 out in front. So I'm integrating u to the power 1/2, 9 du. So the integral of this becomes 9. Add 1 to the top, makes it 3/2. 3/2. Nine over 1 times 2 over 3, x to the power 3/2. Oh, it's me, u. So inside there, so we have 1/9, and the integral of this is 2/3 u, which is 1 plus 9y. to the power 3/2. So it's 2/27. One plus 9 to the power 3/2 minus 1 plus 0. Ten to the 3/2 minus 1. The 10 to the 3/2 is 10 times 10 to the 1/2. Twenty radical 10 minus 2/27. Let me see. Well, yeah, but only thing left is looking at another formula, which looks the same way, does the same thing. So, any questions? Yeah, I'm not gonna lie. Today, the topic, it's not difficult. Again, it's all algebra. However strong you are in algebra will dictate how easy this stuff is. Because the calculus just gets the ball rolling. And after that, then it's up to you. Actually, let's go ahead and do I have one more example. Let's go ahead and try to play with this one. Not focus. Focus. Find the arc length of the function of the curve in example 2. What was example 2? Example 1. Okay, example 2, the function was x cubed over 12 plus 1 over x. Oops. Let's find it. And the starting point is a. What's that? That's just plugging this as for 1, and this is, so yeah, that's not a problem. Okay. So the first thing we have to do is, okay, we're trying to find this again. Which we did that in example 2. What did that give us? So the 1 plus f prime of x squared to see how we did that, refer back to example 2. So we have this part. So we have L equals the integral a to b of the square root of x squared over 4 plus 1 over x squared squared dx. Oh, yeah, bounds 1 to 4. So we have x squared over 4, 1 over x squared dx. So again, it's the new formula is the same formula, just instead of x, they put t's. What's the integral of this first one? That's plus the integral of this one. What's the integral of there's going to be x negative 1 over negative 1, which makes it minus 1 over x. U over 12 minus 1 over 4 minus, oops, we can't do that. That was 1 4. Okay. Yes. Yes, 1 4. Yes. Woo. 1 over 12 minus 12 over 12. Actually, here's the thing what they're trying to say in the second. It just finally hit me what was different about it. Once we had this part here, we're changing it from L to S of some function t. So we're changing L deals with X. Now we deal with T's. Because once we get to the integral part, we get to this part, we have our formula for the length. We have t cubed over 12 minus 1 over t. So if we just looked at the end point, if we just looked at that point, 4 cubed is 64. Get a common denominator. So I need to have 3 and 3. So it's 64 over 12 minus 3 over 12, which equals to 61 over 12. Where's the other point? Minus, that should be plus. Okay. So the difference is this. You go from 1 to x. Yes. Yes. Okay, well, I'm in class right now. Yep. Because here, in our example, when we integrated this, we got, what we get? We got t cubed over 12 minus 1 over t. And that would give us x cubed over 12 minus 1 over x 1/12 minus 1 over 1. Yeah. Okay, this is the difference. X cubed over 12 minus 1 over x. That's still good. And this becomes negative 11 over 12. That is that's the difference. It just hit me. Because we took the original function we had. We changed everything from x to t, integrated it. We got this. But notice our bounds didn't go from a to b like we had, didn't go from 1 to 4. Instead, since we changed it to t, it's going from 1 to x. Now, when we do the integration, we first do it with respect to x, then we do it with respect to 1. And so now we're left with this formula here. That part is the same we've used to have. But because of this, all we have to do now is plug in our endpoint. Because you see, it all automatically starts at 1. And you can go to any x you want to now. You're not limited, because in the past, in the earlier examples, we had a closed bound. Now we're going from a to whatever n's going to be. So all we have to do, once we finish all this thing, all we have to do is now put our new endpoint, plug that in there. We have 64 over 12. Make it common denominator. So we have 64 minus 3 plus 11, which is the same answer we got earlier. But the beauty is we're not limited. We can say I want to know what it is when it's 7. So it gives us a general formula for any value x we want to put in there. I'm sorry, it just finally hit me the importance of that last formula. And that does it. That's section 3 of chapter 6. Again, it's not impossibly difficult. It's just that it's very algebra intensive. That's yes. Yeah. Definition of arc length. Let f of x be a continuous smooth function from on a closed interval AB. The length of the arc, or the arc length of the curve f of x from point A to point B is the value of the integral, what we've been dealing with.